All right, so does anyone have any questions?
Yeah, I have a question on the first one.
Let me guess. Let me guess. Do you kind of want to know what the final temp is and how to calculate the specific heat capacity of lead?
Yep,
Okay. Well, the
you
final
got it.
temp is the same as the thermal equilibrium temp. So that would be that 26.32 degrees Celsius. To calculate the specific heat capacity of lead, you do something like this to begin with. You calculate the amount of energy that the water absorbed. And so I use 1 calorie because it's exact. The problem says it's 15 grams. And the final temp is 26.32. The initial was 22.50. So when we multiply these together, it looks to me like 26 minus 22 is around 4. So the answer should be around 60, but a little less, right?
The only USPS in Calumet City.
Okay, so I just got 357 on my calculator. Do I believe my calculator?
Yeah.
Really?
I mean, well, I mean, I guess if you estimated it as well, but
I estimated that it should be a little less than 60, and I got 357. Should I believe my calculator?
oh no.
No.
So I didn't hear the estimate.
Now I got my calculator, I redid it, and I got 57.3 grams. Do I go ahead and believe my calculator now?
Yeah.
Yeah. Okay. Now, something that you want to do when you do these calorimetry problems is you want to do that the sum of Q's is equal to 0. And we're going to make the assumption that the only thing we have going on for us is the water and the lead. So that means that the Q of the lead plus the Q of the water is equal to 0. That means the Q of the lead is equal to negative Q of the water, which in this case means minus 57.3 calories. So this means that the lead released 57.3 calories of heat, because negative means exothermic, and energy, or heat, I should say. So are you okay with all of that?
Yeah.
Everyone okay with all that? Give me a thumbs up if you are. Okay, so now we're going to go ahead and use this. Now notice I am putting lead down for each of these things because they are not the same as they are for water. So here we get the heat capacity of the lead is going to be the Q of the lead over the mass of the lead times the change in temp of the lead. And in this case, it's minus 57.3 calories. And the mass of the lead, according to the problem, is, I'm looking at the problem real quick. Oops. Am I sharing with you guys?
Yeah.
Okay. The mass of the lead was 27.3 grams. Now the final temp of the lead is 26.32 degrees Celsius, but the initial temp was 98.90 degrees Celsius. So we don't put the larger number first, we put the final number first, always. Now this is going to end up being minus 57.3 calories over 27.3 grams. And when I do this 26.32 minus 98.90, I get negative 72.58 degrees Celsius. So I have a negative divided by a negative, which is going to give me a positive. And 27 goes into 57 two times. 2 over 72 is more than 2%. So I'm going to have to say 0.02, but a little bit more. So maybe 0.03, something like that. But between 0.02 and 0.03, right? And so I get 0.0289, and the units are calories, grams, and degrees Celsius. And there's your specific heat capacity of the lead. Any questions about that? Or are we good? If we're good, give me a thumbs up. Are we good on? Okay. Now, Harry, you said you had another question. Why don't we go ahead and take that, and then we'll see if Ann or Jackie have a question.
Yeah. I guess the next one would be what number is this?
Pardon me?
I just trying to figure out the number of the question.
Well, just what does it begin with? What are the words?
It's 3 45-gram ice cubes.
3 45-gram ice cubes are dropped into 500 mils of tea, which has an initial temp of 20 degrees Celsius. Assuming the specific heat capacity of the tea is 4.2 joules, what is the final temp of the tea when thermal equilibrium is reached? What is the system and the surroundings based on your assumptions? And if there is ice remaining at thermal equilibrium, what mass remains? And wouldn't the tea be better if ice cubes were made of tea? I think we should start with the last question first. Absolutely, because if the ice cubes were made out of tea, when they melt, your tea wouldn't become diluted. Does everyone agree? If you agree, put a thumbs up. Now, there is one place in town I know of that has ice cube coffee, iced coffee cubes, and that's Ramone's over by the hospital. But they don't have them all day long. They run out. So I'm just saying, if you want iced coffee, go to Ramone's early in the day. Okay, so let's take a look at this. First of all, I'm going to calculate the Q needed to melt 3 45-gram ice cubes. Now they're already at 0 degrees Celsius, which means all the energy can go into melting. Now the heat of fusion, I wish there was an abbreviation for this, but there isn't, is 333 joules per gram. That's not something you need to memorize, but I happen to know it. So if we have 3 ice cubes times 45 grams per ice cube times 333 joules per gram, that would give us the energy needed to melt the ice cubes. So roughly speaking, 3 times 333 is 1,000, isn't it? And 1,000 times 45 should be close to 45,000. And I get 44,955 joules. Now, the 3 is exact. The 45 has 2 zig figs, and the 333 has 3 zig figs. So this is only really good to there. Now I'm going to calculate the Q the T can release when it goes from 20 degrees Celsius to 0 degrees Celsius. So that's the maximum amount of heat that the T can give up. So here the Q of the T is equal to the specific heat capacity of the T times the mass of the T times the change in temp of the T. Now this problem says that It's 4.2 joules per gram degree Celsius. Now, they don't give us the mass of the tea, so we're going to have to make an assumption. What is the density of water? It's 1 gram per milliliter, approximately. Good to 2 zig figs. So what do we think the density of the tea is? Should be the same.
Actually, I think that they gave us that there's 500 milliliters of tea.
Right. But they don't give us the mass.
Oh, okay.
So we're going to take that 500 milliliters and multiply by 1.0 grams per milliliter. Okay? And the change in temp of the tea is going to be from 0 to 20. Okay, so let's find out how much energy the tea can give up. And notice this number is going to be negative, which means the tea is releasing heat. When it releases heat, it's going to melt the ice. Now, 4.2 times 20 is going to be what? 8.4 or 840? And 840 times 500 is going to be, well, I don't know. I got to think about that. That's half of 840, which is 420. So probably 42,000. So 4.2 times 500 times 20, and I get negative 42,000. And this is only good to hear. Joules possible from the tea.
Oh, there's something we can't see here. There's something. Oh, there it is.
Is my paper down too far?
No, there's just some weird camera thing going on.
Oh, really? I'm looking at the problem, not the not what's on
Oh,
the
no,
board.
wait.
Take a look.
Oh no, we can see it fine now.
Okay. So this is needed to melt the ice. And this is the amount of energy that the tea can give up. So look at these two numbers. Is there enough energy that is going to be produced from the tea to melt the ice? If you think there is, oh, you already voted no. There's not enough. You need to release 44,955 joules to melt all the ice. So we would say, first of all, there is not enough heat from the tea to melt all of the ice. So at thermal equilibrium, there will be ice and tea at 0 degrees Celsius. So what is the final temp? Zero degrees Celsius. All right. Now, the next question is, so if there is ice remaining, how much is remaining? So we have 42,000 joules available to melt the ice. And we know that 1 gram takes 333 joules. Can I use the heat of fusion upside down? Absolutely. So how many times does 333 go into 42,000? It goes in 3 times 42 times. And 3 times 42 is roughly 120. So let's find out what we get. 42 divided by 333, and we get 126 grams melt. Now, really, when we round, this will become 130, but we're not going to round yet. Now, we start off with 45 grams times per cube times 3 cubes, which is 135 grams to begin with, and 126 melt. So we have 135, and this is good to the 1,3, right? Minus 126, and that's good to the 1,2. So here, this is technically only good to the tens. And so this 9 doesn't count. So what should we write as our answer? We don't get to keep that, but we do get to keep that. So if this is the place we get to keep, what do? We look to the right and see what number it is. I look to the right, what do I see here? A 9. So what does this number become? A 1. And what does this number become? A 0. So 10 grams is remaining. So if you're all good with that, give me a thumbs up. This is problem number, I don't know what problem it is. This is the one, this is the ice problem, August. All right, who's next? No next?
This might be a really silly question. I feel like I'm making a really silly mistake somewhere.
Is it a
and
homework
then-
problem?
Yes, it is a homework problem. It's number 1.
Number 1. So what's your question on that?
My question is, I think I'm doing everything right, plugging in everything in the right place, but then I end up getting 670.6 joules per gram Celsius, which is obviously not the right answer.
No, it's not the right answer. So what
and
you
what's
need to
weird
do
is-
to be able to do this one is, here's the first thing I do for this one, August. This is the first thing. What I'm doing here is I'm calculating the amount of energy that the water absorbs.
Yes. Yeah,
And I
that's what I
get
got. for that as well.
57.3 53 point, this should be calories. Okay.
Yeah, that's the answer that I got for that part as well.
And then because of the law of the conservation of energy, we can sum the Q's and it equals 0. And we assume that our system and surroundings is simply water and lead. So Q of the lead plus Q of the water is 0. Q of the lead is equal to negative Q of the water. So Q of the lead is minus 57.3 calories, okay? And then you use this to figure out the rest. So here, Q of the lead is the specific heat capacity of the lead times the mass of the lead times the change in temp of the lead. When I switch this around and focus instead on specific heat capacity of the lead, I get Q of the lead over mass of the lead, change in temp of the lead. This is minus 57.3 calories. This is 27.3. And this, we put the final temp first, and then the initial temp second. And so we get a negative change in temp. So a negative energy over a negative change in temp because it's a positive value, and we get positive 0.0289 calories per gram degree Celsius. So I'm not sure where you made your mistake, August, but I'm guessing that you might have done this in joules. Is that right?
I did it in calories.
Oh, you
And
did
then I
in
converted
calories.
And then I converted it to joules at the end.
Well, if we convert this to joules at the end, we'd multiply by 4.184 joules per gram, joules per calorie, and we still wouldn't get a large number like you got.
Okay, I don't know if this fully accounts for my error, but I think I put the wrong temperature for I think I put the wrong temperature for the final temperature. I think I may have put the final.
Did you do something like, instead of dividing by what looks like around 72, you divided by about 4? Right
I
here?
think I put the initial temperature for the water instead of the final temperature for the water.
Right. That means you divided by 4 instead of 72.
I was doing 22.50 minus 98.90 as
Right.
opposed to 26.32 minus 98.90.
Right. And so here, this difference is about 72. The difference from the other one is about 4. So you divided by 4 instead of 72,
Okay.
which is why your number was so large, because you didn't divide by big enough of a number.
Okay.
And so that is why I do this, because
Yeah.
I am focusing on the change in temp of the lead, not the water. So in this case, these little labels at the bottom can help you.
Yeah. Okay.
All right, who's next? Okay, we're just gonna do some problems from the back of the book.
Actually, I had a question I actually had two questions. The first one was the second problem on the homework.
Second problem on the homework. Insoluble lead 2 bromide precipitates when solutions, that one?
Yeah.
Okay. So here I'm going to draw a quick picture. We have 200 milliliters of 0.75 molar lead 2 nitrate. And we have 200 milliliters of 2.00 molar, 1.5 molar sodium bromide. Now, if we do a real quick calculation, 0.75 times 200 and 200 times 1.5, you can see that this is 150. And this is 300. So here, if we look at the lead, the amount of lead in here is 150. I'm not going to give any units to it. Here, the amount of bromide is equal to 300. And when we do the reaction, we actually need 2 bromides. So what this means is that we have the stoichiometric amounts that we need for the reaction to go to completion with no leftovers. Okay? So we're supposed to calculate the enthalpy change in kilojoules per mole. Which means I'm going to need 2 things. I'm going to need the Q in kilojoules, and I'm going to need the moles. So to calculate the moles, I'm going to take my 200 milliliters, multiply it by 1 liter per 1,000 milliliters, and multiply that by 0.75 moles of lead nitrate, lead 2 nitrate per 1 liter of solution. And then I'm going to multiply by 1 mole of lead bromide per 1 mole of lead nitrate. Because the balanced reaction, as you can see from the way it's written, is there's 1 mole of lead 2 nitrate to 1 mole of lead 2 bromide. So this will tell us how many moles of lead 2 bromide we have. And it looks like it's going to be 5 into 75, which is a 0.15 mole of lead bromide, if I did that right in my head. Yep. Okay, so that's how many moles of lead 2 bromide. Now to calculate the heat, we end up with 400 milliliters of solution. And in this case, they say the temperature of the mixture rises by 2.44 degrees Celsius. So I don't know what the initial temperature here is and what the initial temperature here is. I'm assuming they're the same. And the final temp, whatever it is, it's equal to the initial temp plus 2.44 degrees Celsius. So since these both start at the same temp, and since their specific heat capacity is the same, and their densities are the same, I can work this as one problem where we start off with 200 mils at one temp and end up with we start with 400 mils at one temp and end up with 400 mils at 2.44 degrees Celsius higher. The mass of this is going to be 200 mils times 1 gram per milliliter, which is 200 grams. And the same goes for this one. So when we go for the heat that the solution absorbs, it's going to be specific heat capacity of the solution times the mass of the solution times the change in temp of the solution, which is going to be 4.2 joules per gram degrees Celsius. Remember, the K and the degrees Celsius are interchangeable. The mass is 400 point grams, and the change in temp is 2.44 degrees Celsius. So here I get for the Q 4.2 times 2.44, which is about 10, times 400, which is about 4,000. And I get 4,099.2. And this is only good to the 0 here. So if I were to round, I'd round to 4,100 because of this 4.2. So that means the specific heat capacity per mole is 40. Oh, and I do want to do one more thing here. I'll do it down here.
I think there's also some problems like with the camera because I can't like see the bottom portion of your work right
It's
now.
like you're writing underneath the bar.
Let me see what's going on here. I wonder if I'm moving the paper around or.
There was kind of a reflection of the bottom quarter of the paper.
Maybe it was the sharing thing. Is that in the, is that in the way now?
We can see it now.
Can you see the bar that says mute and all that stuff?
No.
Huh. Interesting. Okay. At any rate, and here I'm going to multiply by 1 kilojoule per 1,000 joules because I believe the question was in kilojoules per mole, wasn't it? Yep, enthalpy change in kilojoules per mole. Okay, so $4,099 divided by 1,000 is 4,000 is 4. 4 divided by 0.15 is 12. Oh, I must have did something wrong. Let's see. 4 divided by 0.15 is, 0.33 would be 12. So 0.44 was 24. So we get 27 kilojoules per mole. And there's your answer. So we had to break this up into two parts. One, calculating the amount of energy that the solution absorbed. And here, calculate the moles of lead 2 bromide. And I would say that this answer is still incomplete. And I'll tell you why in just a moment. This says calculate the enthalpy change for the precipitation of lead 2 bromide in kilojoules per mole.
It's happened again.
So here's the thing that I'm gonna, did you say it's happening again?
Oh, yeah. Sorry, I forgot I was unmuted. Yeah, well, it seems to be fine now, but it's like when there seems to be this weird bar that like, oh, there it is again. It's like reflecting the paper, but it freezes, so we can't see what you're doing underneath it.
Huh. Well, you just let me know when that happens, and then you let me know when it's taken care of, because I don't really see anything going on my end.
I don't know
Okay,
what's
so
causing it.
here, remember the Q of the solution is equal to 4,099.2 joules. And I'm going to go ahead and multiply by 1 kilojoule per 1,000 joules, which is 4.099 kilojoules. Okay, so in our reaction, you got the solution, but you also have the reaction. So really we have the Q of the reaction plus the Q of the solution is equal to 0, which means the Q of the reaction is equal to negative Q of the solution, which means the Q of the reaction is minus 4.099 kilojoules. And then you divide that to get the change in enthalpy per mole. You take that 0.4099 kilojoules and divide it by 0.15 mole, and you get 27 kilojoules per mole. And the reaction is exothermic. How do we know the reaction is exothermic? And the answer is we know the reaction is exothermic because the solution heated up. So this is a better answer than before. Plus 27 was how much energy the water absorbed per mole of reaction. But we really want to know the amount of energy released per mole of reaction. Okay, any questions about that? Okay, Jackie, you said you had 2. What's the second one?
The second one was the last one because I was running into some problems like when I was trying to rewrite the equations.
Did
And
you
like-
reload what do you have for the equations?
So like I did make that correction for the oxygen. The coefficient was supposed to be 1/2,
Okay, good.
but there was a problem with the hydrogen instead.
Well, let's
When
take
I-
a look here.
yeah.
This is our goal, right? That's the goal. So I'm going to use the first equation and multiply it by 2 to get 2 carbons plus 2 O2s.
There's that weird reflection thing again.
It's doing it again.
Yeah, but it's up in the top now. Where you're writing that formula.
Huh. That is hunky weird. Let me see now.
Oh,
Has it gone away?
yeah.
Yeah, it's work.
You know, as soon as I'm looking at, on my computer, I'm looking at the web browser so I can read the problem. And it seems to happen when I'm looking at the web browser and not at what you guys are seeing. So at any rate, there's that. And this would be 2 times negative 393.5 kilojoules. Is that right?
Yeah.
Okay. Now I'm going to switch back to my web browser so I can read the problem. So we might have that problem again. Now I'm going to take the last equation, number 3, and I'm going to write it in reverse. So I'm going to have 2 CO2. If it happens again, let me know.
There's a little bit down at the bottom, but it's a really skinny bar, so it's not
Oh,
obscuring
down
anything with your
here?
fingers. Yeah,
Where my hand is?
yeah, but it's only like a millimeter thick.
Okay. As long as it's not bothering you guys up here, then we're good. So here I'm going to have to do the negative of negative 1367.5 kilojoules. Okay. Now, if I take a look at what I have written here so far, can you see that these two are going to cancel? And here, 2 of these will cancel with 1 of these, or 2 of these, I'm sorry, and leave 1 left over. And you can see we have 3 H2O left over that we want to get rid of, right? So I'm going to take the second reaction and multiply it by 3. So when I multiply the second reaction by 3, I get 6 H2 gas plus 3/2 O2 gas gives you 3 H2O liquid. And we get 3 times negative 571.6 kilojoules per mole. Okay, so that means that these will go away. And here I have 3/2 and 1, so this turns into 1/2 O2. Oh, and I see we get 6 H2. And that's not what we want, is it? So we get 2 carbons plus 6 H2 plus half O2 gives us 1 C2H5OH liquid. So we got to find out which one of these reactions is not balanced. This reaction here is supposed to be 2 H2 gas plus 1/2 O2 gas. It's supposed to be H2 gas. This is supposed to be only 1.
I think the bar is blocking the equation again.
Okay, so the second reaction should read as follows. Instead of 2 H2, it should read H2 gas plus 1/2 O2 gas gives you H2O, and it should be minus 285.8 kilojoules. So I'm going to go in and correct that right now. Edit. Get rid of that. And 285.8 kilojoules. Save it. Let's see, what class am I in right now? 86. Let's see if it worked. Why is my computer so slow? Because it's old, that's why. So let's see if it took. Yep, it worked. So I'm going to change to the other class and change it real quick in that one. Has everyone voted yet? Early voting. Do your patriotic duty and vote. Darn it. $285.8 and get rid of that too. And then save. Okay, so let's try this problem again. Now that we have all the correct equations. Or do you want to just try it yourself, Jackie, now that you have the correct equations?
I think I got it from here.
Okay, cool. All right. Who's next? Okay, then in the last few minutes of class, I want to talk about standard enthalpies of formation. So we're going to look at these problems here. Standard enthalpy of formation. So this is the amount of change in enthalpy for standard formation of a substance. So to do this, you have to understand what the standard state is for all the elements. For the standard state for the elements, this is going to be at 25 degrees Celsius, which is about room temperature, and 1 atmosphere of pressure, which means basically about room pressure. So the ones that are liquids at standard state are only 2 of them. Bromine is a liquid, and mercury is a liquid at room temp. The reason you want to remember the liquids instead of anything else is because it's a small list. The ones that are a gas at room temperature are hydrogen gas, nitrogen gas, oxygen gas, fluorine gas, chlorine gas, bromine, oh, not bromine, bromine's a liquid, helium, neon, argon, krypton, xenon. I'm trying to remember if anyone else is a gas at room temp. Let me take a quick look at the periodic table. Oh, I forgot radon. So these are the gases. The solids are everything else. Sodium is a solid. Carbon is a solid. Copper is a solid. Phosphorus is a solid. So it's easiest to remember the liquids and the gases. So those are their standard states. To write a balanced equation for the formation of something from its standard states, here are the steps that you go about doing it. First of all, you write the substance where you want the reaction. So here's the substance that you want. Then you take a look at all the elements in there and you separate them. So this has calcium in it, carbon in it, and oxygen in it. And then the next thing I do is I fill in those that should come in pairs. And the ones that come in pairs are the Honkelbriefs. Honkelbrief. So if one of these elements is a hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, or fluorine, I'm going to put a little 2 behind it. Then I put the standard state in. So solid for carbon, gas for oxygen, and solid for calcium. And then you have to balance the reaction. And a standard enthalpy of formation reaction, by definition, is the formation of exactly 1 mole of this. So that means I cannot change the coefficient in front of this. I can only change the coefficients out here. So 1 calcium, that's good. 1 carbon, that's good. 3 oxygens, 2 oxygens, I have to put a 3/2 here. So that's the standard enthalpy of formation of calcium carbonate. And then to look it up in the book, we look in the appendix. And normally for things like this, you look them up by the name of the first element. So that'd be calcium. So here we can see right here, calcium carbonate, calcite. It's minus 1,207.6 kilojoules per mole. Okay. So any questions about how to write a standard enthalpy of formation reaction? Are we good? Thumbs up if we're good. Okay, now it's your turn. Write the standard enthalpy of formation reaction for the formation of 1 mole of magnesium oxide from its elements in their standard states. And then look it up in the index or the appendix and see if you can find it. When you're done, give me a thumbs up. That's where you start. Separate the elements. Put in the Honkelbriefs. Put in the states. And then balance. So there's the reaction. And minus 601.24 kilojoules per mole. Any questions on that one? All right. What is the standard enthalpy change for the reaction of 2.4 moles of magnesium with oxygen? So here we just write 2.5 mole of magnesium times negative 601.4 kilojoules per mole of magnesium. And I know it's per mole because there's a 1 for the coefficient. So here we have 2.5 times 601, which comes out to what? 1,200, 1,500 minus 1,500 kilojoules. What would this be if the question were instead asked about for 2.5 moles of oxygen? So if this question were asked instead the standard enthalpy change for 2.5 moles of oxygen, it would look like this. And this would be 1/2 mole of oxygen, because in the balanced reaction up there, it's 1/2 mole. So that means the answer would be 3.0 times 10 to the third kilojoules. Are there any questions about what I've done here? If so, raise your hand. Okay, let's do another one. So this is a standard enthalpy of formation. The Romans used calcium oxide to produce a strong mortar to build stone structures. Calcium oxide was mixed with water to give calcium hydroxide, which reacted slowly with carbon dioxide in the air. To give calcium carbonate. And calcium carbonate is pretty much the same thing that seashells are made out of, and coral. So the calcium hydroxide reacts with CO2 to give calcium carbonate and H2O. Calculate the standard enthalpy change for this reaction. So for this is what they want you to do. So I'm going to leave this reaction right here. To do this, we need the enthalpy of formation for calcium hydroxide, CO2, calcium carbonate, and H2O gas. Now I know for H2O gas, it's minus 241.8 kilojoules. And here I'm just going to put kilojoules up here so I don't have to put it down here. And for calcium compounds, I can look these up in the index or appendix one by one. And since they all have calcium in it, they should all be in a similar place. So calcium hydroxide solid is minus 986.09 kilojoules. Calcium carbonate is minus 1,207.6 kilojoules, and CO2, I believe, is 393.5 kilojoules. Okay. So these are the things I need. And the way we do this problem is this. The enthalpy of reaction is equal to the sum of N times the enthalpy of formation of the products minus the sum of N times the enthalpy of formation of the reactants. So I'm going to bring this down here because I'm going to need the room to do this. So the way this looks is this way. The enthalpy of the reaction is equal to, I'm going to do the products first because they are first. So here we have calcium carbonate. And this looks like it's a balanced reaction, but I'm going to be careful about how I do this. This N means the number of moles. So how many moles of calcium carbonate do we have? 1. So 1 times the enthalpy of formation of calcium carbonate solid plus 1 times the enthalpy of formation of H2O gas, and then minus 1 times the enthalpy of formation of calcium hydroxide solid plus 1 times the enthalpy of formation of CO2 gas. So I'm writing this out with the great deliberation to show you exactly how this gets put into here. Now, where do these ones come from? They come from the balanced reaction. Now, when we fill in the rest of this, we can ignore the ones, and we basically have calcium carbonate is minus 1,207.6 kilojoules. H2O is negative 241.8 kilojoules. Calcium hydroxide is minus 986.09 kilojoules. And then CO2 is minus 393.5 kilojoules. So when we do the work here, you can see that these two roughly add up to minus 1,440. These two add up to minus, I don't know, 1,380. So you're going to have a difference of around 40 or 50 or something like that. So let's put this into our calculators very clearly. 1207.6 minus, or I'm going to put plus 1207.6 plus 241.8. And so here I get 1449.4, and I'm going to put a negative here. And then I get 986.09 plus 393.5. And here I get negative 1379.09 kilojoules. And so that becomes minus 1449.4 kilojoules plus 1379.09 kilojoules. And this is the hardest part about this problem, is keeping track of the pluses and minuses. And I get negative 70.31 kilojoules. And going through all of this, this is good to the 10th, this is good to the 10th, this is good to the 100th, this is good to the 10th. Since I'm just adding and subtracting all of these, I'm going to use the one that's the least precise, which is the 10th. So my real answer is negative 70.3 kilojoules. Any questions about how I did that? This is the kind of work I would expect to see on your exam. Step by step, a nice list of the enthalpies. Now, which of these should you memorize for the exam? Anyone have any ideas? I'll take that as a no. And the answer is, don't memorize any of them. There's too many. I will give you the ones you need. Fair enough? Okay. Any questions on this one? Calculate the standard enthalpy change for this reaction. Now, how much energy is evolved or absorbed as heat if 1 kilogram of calcium hydroxide reacts with a stoichiometric amount of CO2? So stoichiometric amount of CO2 means the precise right amount so that all of the calcium hydroxide reacts. And to do that, we would do this. We would take our 1.00 kilograms of calcium hydroxide. We turn that into grams of calcium hydroxide. Turn that into moles of calcium hydroxide. And then turn that into since it doesn't say kilojoules of energy, it just says energy, then I turn that into kilojoules. So that's the way, this is the way this would look. And the molar mass of calcium hydroxide, I have to figure out very quickly. Calcium is 40.08. Oxygen is 16, and two of them would be 32. Hydrogen is 1.01. So we get 74.1 grams of calcium hydroxide solid per 1 mole of calcium hydroxide solid. And then we multiply by the answer we got previously, which was minus 70.3 kilojoules per 1 mole of calcium hydroxide solid. So we can see that this answer is going to come out being negative because there's only one negative number in all of this. 74 goes into 73 about 1 time, and 1,000 times 1 is 1,000. So the answer should be close to 1,000, but not quite because of this 73 and 74. And so I'm going to guess that the answer is going to be closer to the negative 950 kilojoules. So let's see what we get. And we get 949 kilojoules. Dang, I was close. I said 950. See how close that was? If you're impressed, give me a thumbs up. If you're not impressed, what does it take to impress you? Okay, are there any questions about how to do this problem? I think I have another one that I'd like to do that is similar to this. And let's take a look at it. So this is still standard enthalpies of formation. So an important step in the production of sulfuric acid is the oxidation of sulfur dioxide to sulfur trioxide. With this formula, SO2 gas plus 1/2 O2 gas gives you SO3 gas. Now, this is not an enthalpy of formation reaction. And the reason it's not an enthalpy of formation reaction is because this is not an element. Enthalpy of formation reactions have only elements as reactions or reactants. So this is a reaction. Formation of sulfur trioxide from the air pollutant sulfur dioxide is also a key step in the formation of acid rain. Use standard enthalpies of formation to calculate the enthalpy change for the reaction. So what we're going to want to do here to calculate the enthalpy change for the reaction is make a list of substances. We have SO2 gas. We have a O2 gas, and we have SO3 gas. And the change in enthalpy of formation for each of these in kilojoules, we look up in the back of our book. And on the test, these would be given to you. So on the test, I would give you the one for sulfur dioxide. I'd give you the one for sulfur trioxide, but I would not give you the one for oxygen. That's one you should know. So it turns out that there's about 100 enthalpies of formation that you should know. I'll go over those in just a moment. Okay, so I'm not going to give it to you for oxygen. But what I want to do is I want to write the enthalpy of formation reaction for each of these. So for SO2 and for O2 and for SO3, I want you to write all three reactions out. And when you're done, give me a thumbs up. And if you can't get it, still give me a thumbs up because you're ready to see the answers. So kind of a hint for this one, we write oxygen and sulfur. Okay, I'm hearing crickets. Okay, we got one person who's done, two that are done, three that are done. How you doing, August? Okay?
I think I'm gonna need to hear the answers, but
Okay, so we're going to do these one by one methodically. First thing you do is you look at the elements in the product and separate them. So sulfur and oxygen. Then you take care of the Honkelbrists, the ones that come in pairs, and only oxygen does. Then I like to put the standard state, oxygen's a gas, sulfur is a solid. And then you balance it. One sulfur, two oxygens, this one's done. And this is the energy change for that reaction. Okay, so now let's do this next one. What are the elements in O2? Only oxygen. Does oxygen come in pairs? Yes, it does. What's its standard state? It's a gas. So this is the reaction. So how much energy does it take to take O2 gas in its standard state and turn it into O2 gas in its standard state? 0. So the book tells you that the standard enthalpy of formation for any element in its standard state is 0. So when I say you should know 100 different enthalpies of formation reactions, it's for all of the elements. So for instance, this is 0. This is 0. This is 0. So give me a thumbs up if you're getting tired of this. This is 0. This is 0. Oh, come on. You guys have to be getting tired of this. This is 0. Okay, these are all 0 because you're doing nothing. All right. So how about this one? What are the elements in SO3? Oxygen and sulfur. Oxygen always comes as pairs and as a gas. Sulfur is a solid. But to balance this, we have one sulfur, two oxygens, three oxygens. So you have to put a 3/2 here. So these are the reactions that we're interested in. Okay. So now it tells us use standard enthalpies of formation to calculate the enthalpy change for the reaction. So we're going to write for the reaction, it's equal to the sum of N times the change in enthalpy of formation for the products minus the sum of N times the change in enthalpy of formation of the reactants. And remember, here's the balanced reaction. We can just barely see it right there. There's the balanced reaction. So when I fill it in, it looks like this. Only one product, 1 times the change in enthalpy of formation of SO3 gas. And I'm going to end the bracket, and I'm going to start a new bracket for the reactants. And here we have 1 times the change in enthalpy of formation, of SO2 gas, plus this little thing means the summa, which means we add together these values plus 1/2 times the enthalpy of formation of oxygen gas. Okay, now we plug the numbers in, and 1 times negative 395.77 kilojoules is negative 395.7 kilojoules. 1 times negative 296 is negative 296.84 kilojoules. And then plus 1/2 times 0 is 0. So what's going to happen here is I'm going to cross that out because that's 0. I'm going to take this negative and negative, make that a positive. And you can see that the difference here is about negative 100. So we have 395.77 and 296.84. And the difference is 98.93 kilojoules. Okay, so that's the answer to the change in enthalpy. Is it endothermic or exothermic? So if you think it's exothermic, pick go slower. If you think it's endothermic, pick go faster. Endothermic, go slower. Exothermic, go faster. Endothermic, go slower. Exothermic, go faster. And how do we decide this? Oh, and do you see I forgot my minus here? Negative. So endo, go slower. Exo, go faster. Alphabetical order. Endo, go slower. Exo, go faster. And the answer is it's exothermic because it's a negative value. Okay? Now, the next thing we're asked for is draw an energy level diagram to show the relationship between these. So we're supposed to show an energy level diagram that shows the relationship between this and this is minus 296.84 kilojoules. This and this is minus 395.77 kilojoules. And this and we just discovered this is minus 98.93 kilojoules. And off in the back of our mind, we should be thinking about this guy also. And that would be 1/2 O2 gas turns into 1/2 O2 gas, and the change in enthalpy is 0, of course. So we want to draw an energy level diagram with these 4 reactions. And the way I've tried to instruct this before is to tell you to always start with the one of these that has the biggest number. So 395.77 is the biggest number. Since it's a negative, you draw an arrow going down. And this is minus 395.77 kilojoules. Now, what always goes at the head of the arrow? And the answer is the product. So here I'm looking at the second reaction, and I have to write SO3 at the bottom, and I have to write sulfur solid plus 3/2 O2 at the top. Now I've taken care of that one. Now I want to incorporate this guy or this guy. It doesn't matter which one I do. I'm going to incorporate this guy. And can you see that I'm going to end up with SO3? So I need an arrow going down. And this arrow has to be minus 98.93 kilojoules. So it ends up here at SO3. But instead of starting up here at S2 and 3/2 O2, it starts at SO2 and 1/2 O2. And here, this last arrow, you can see I want to end up at SO2, which is right here. And I want to start off here. So I'm going to do this. Now, where does this reaction come into play? And the answer is nowhere so far. I don't really need it, but there are some problems with this. And here are the problems. How many sulfurs do we have on this line? 1. How many oxygens do we have on this line? 3. How many sulfurs on this line? 1. How many oxygens on this line? 2.5. How many oxygens on this line? 3. How many sulfurs? 1. So this guy's missing out something. And the thing it's missing out on is another 1/2 O2. Now, if I take a look at this, how many sulfurs? 1. How many oxygens? 3. Now it's balanced. And this reaction is actually also part of this reaction right here. And it's kind of hard to see, but it's in there. What's really happening here is if I rewrite this, we have sulfur solid plus O2 making this. And then we have, oh shoot, let me think about this. Oh, well, never mind. That should belong in there. So that's your energy level diagram. Okay, that's a tough one. Energy level diagrams are something that a lot of you are going to probably mess up on the exam. All right, this is just another calorimetry problem. But you can see it's a little bit different. Do you guys want to do this? If you want to do this, give me a thumbs up. If you don't, we'll just call it a day. So thumbs up, we do it. Thumbs down, we call it a day. We've only got one vote. Are you all still there? All right, we'll do this one really quickly. 9.36 gram piece of platinum was heated to 98.6 degrees in boiling water, then dropped onto ice. The metal's temperature had dropped to 0 degrees Celsius. It was found that 0.37 grams of ice had melted. What's the specific heat capacity of platinum? So we're going to assume the ice was at 0 degrees Celsius. So all the heat went into melting. So that means we're talking about 0.37 grams of ice times 333 joules per gram. This is the heat of fusion. For ice. So that's how much energy melted the ice. So here, this would be plus 123. And so that when we say Q of the ice melting plus Q of the platinum is equal to 0, Q of the platinum is negative Q of the ice. And so Q of the platinum is equal to negative 123 joules. Now, to calculate the specific heat capacity of the platinum, you're going to need the Q of the platinum over the mass of the platinum times the change in temp of the platinum. And the Q of the platinum is minus 123 joules. The mass of the platinum was 9.36 grams. And the change in temp of the platinum is 0.0 degrees Celsius. So the metal's temp dropped to 0. That's the final temp. Minus 98.6 degrees Celsius was the initial temp. So when we work all the numbers, you can see basically we have 123 divided by 98, or 100, which is 1.23. And 1.23 divided by 9.36 is, I don't know, 0.12. So 123 divided by 9.36 and divided by 98.6, and we get 0.13 joules per gram degree Celsius. And this has only 2 zig figs, so this really should only have 2 zig figs. And so when you have 2 zig figs, 3 zig figs, and 3 zig figs, your answer is 2 zig figs, and there's your specific heat capacity of platinum. And this is a negative, this is a negative, so you get a positive.
Can you move up the paper?
Oh, sure.
Yeah. All right, so good.
Why don't you say something earlier?
Well, you seem focused in it, so I don't want to cut it out.
Okay, so let's look at this again. We're going to assume the ice was at 0 degrees Celsius, so all the heat went into melting. And this is how much heat goes into melting the ice, because the heat of fusion of ice is 333 joules per gram. Now, we want to keep this extra 3 along for the ride, but this really only would have 2 zig figs if we were done. Because of the first law of thermodynamics, we would say that the Q of the ice plus Q of the platinum is 0. So therefore, the Q of the platinum is negative Q of the ice, which is negative 123 joules. And that makes sense to us because the platinum is releasing heat, which is exothermic, and it should have a negative value. So to calculate the specific heat of the platinum, we take Q of the platinum divided by mass of the platinum divided by change in temp of the platinum. And here we see this is a minus 123. And the final temp of the platinum is 0. The initial is 98.6, providing for a negative temperature change. Negative divided by negative gives you a positive, and you get positive 0.13 joules per gram degree Celsius. And this has 2 zig figs because this should only have 2 zig figs. Okay. Any questions about that one? If not, turn on your mics and say goodbye.
Bye, everyone.
Bye.
All right. See you all Wednesday. Exam day.